So my name is Paulo Martins. I'm a PhD student at the University of Lisbon. I'd like to thank everyone for coming, and especially Professor Ingrid for having asked me to come here. I'm going to be talking about the arithmetic challenges of fully homomorphic encryption. If you have any questions during my presentation, feel free to interrupt me. And so, fully homomorphic encryption has been a massive achievement in cryptography. It allows you to encrypt your data, to send this data to someone else who can process it without having to decrypt it. And in the end, they can send you the result back, and you can decrypt this data and have access to the results as if you had processed this data yourselves. However, these new schemes rely on different primitives from traditional cryptography, which raises some questions on what's the best way to implement them. And in this talk, I'm going to try to address the issues that are related to arithmetic. And in particular, I'm going to focus on 3 questions. The first one is, what's the optimal way to represent these ciphertexts? Is there any way in which you can represent them such that the homomorphic operations that we are trying to apply to these ciphertexts have their complexity reduced? So secondly, the operations that these homomorphic systems provide to a user are typically operations over cyclotomic rings, and most real-life applications operate on the reals. And so my second question is there any seamless way to map these real-life applications onto these cyclotomic ring operations? And my third question is, homomorphic encryption provides you with a way to protect the confidentiality of your data. What if we also want to protect the confidentiality of the algorithm that the homomorphic evaluator has to apply to this data? Can we also protect it? So I'm going to start by giving a brief overview of the Fan-Vercauteren crypto system, which I believe most of you should be familiar with it. And so most operations take place in a cyclotomic ring, which is a ring which can be seen as a set of polynomials where the additions and multiplications are defined modulo a cyclotomic polynomial, which is a polynomial of degree phi of m, where phi is Euler's function. Ciphertext corresponds to pairs of elements of this ring. So there are 2 polynomials, C0 and C1. They can be interpreted as a polynomial, as the coefficients of a polynomial in Y, such that when I evaluate this polynomial at Y equals to S, where S is the secret key, it corresponds to a polynomial with small coefficients, I'm capable of decrypting the message. The message space is that cyclotomic ring with the coefficients reduced modulo 2. So after doing this operation, I'm going to get the message that I have encrypted scaled by a factor of q over 2, where q is this modulus plus some noise. You can see that when I add 2 ciphertexts coefficient-wise, this property is maintained in the sense that when I evaluate it at y equals to s, I'm going to get the addition of the ciphertext, the addition of the message that the ciphertexts were initially encrypted, plus some noise. This noise is going to grow, and as I apply homomorphic operations, the noise is going to continuously grow. And at some point, I want to be able to do decryption, and that's going to limit the amount of operations that I can do. To do multiplication, I can also do the multiplication of the 2 polynomials in Y, but as a result, if I were to apply decryption to it, I'd have a factor of delta squared there. So to prevent this from happening, I do this multiplication over the integers, and then I scale by 2 over q, which is going to eliminate one of those deltas. And then I reduce the result modulo q, and I'm going to get a ciphertext that has 3 elements. It's ct0 plus ct1y plus ct2y squared. And if I evaluate this polynomial at y equals to s, I'm going to get the decryption, which is the product of the 2 messages. However, to prevent the degree of the ciphertext from continuously growing, I'm going to apply an operation called relinearization that converts this ciphertext, which is of degree 2 in y, back to a ciphertext that's of degree 1 in y. To do this, I multiply ct2 by an encryption of s squared, and I add the result back to ct0 and ct1. I cannot do this directly because ct2 is uniformly random over RQ, and that would mean that if I were to multiply by 10 encryption of S squared, the noise would grow a lot. To prevent this from happening, I define two functions that I call D and P, and these functions produce vectors of polynomials, such that when I compute the inner product between these two vectors, I get the product of A and B, with the additional constraint that the decomposition of A is a vector of polynomials, such that the norm of these polynomials is small. And now I can encrypt, instead of encrypting S squared, I encrypt P of S squared, and when I multiply D of CT2 over here by these encryptions of S squared, now this will have a small norm, which when multiplied by these encryptions is not going to increase the noise a lot. And so I can convert that element back to a two-element ciphertext, and the decryption will be the same. The noise will have increased a little bit. So part of the improvements that I'm going to propose later in this talk are going to be based on the residue number system. The residue number system, it's a representation system that allows you to break down large integer arithmetic into smaller channels. So over here I have an example. In the first row, you can see that I'm computing the convolution between an image and the kernel modulo 210 to obtain this result. However, since 210 factors into 7, 6, and 5, I can compute the remainder of the division of this image by 5, 6, and 10, and then compute these operations, modulo 5, modulo 6, and modulo 7. And I get 3 results, which, when combined, can produce this initial image. And the advantage of this is that instead of having to handle very large integers, that is something that is difficult with current computer architectures, I only need to handle these smaller channels, which take a few cycles to execute in a regular computer architecture. When this logic is applied to our scheme, we can choose a queue. There is the product of Q1, Q2, etc., Qk. And when I have an element there, A, to get an RNS representation, I compute the remainder of the division of A by Q1, Q2, etc., and I get an array of polynomials, and I can do additions and multiplications of these polynomials coefficient-wise, and I have, they correspond to additions and multiplications modulo Q. There is this formula that allows me to convert back these residues back to RQ. Over here, this Qi over Q is just the modulo inverse of this modulo Qi. In practice, we don't do this because we don't want to get back to that system, because that would mean we need to process large integers again. We typically target another residue number system basis, where I choose modulus B that factors into B1, B2, etc. And I evaluate that formula, where I add A modulo Q, modulo each one of these BI. This can be sometimes challenging because there is this alpha here, and sometimes I can avoid its computation. I insert an error that can be handled later in the computation, but there are methods either to approximate it or to compute it exactly, but then they are more expensive computation. And so this is the state of the art in the application of the residue number system to the Fan-Vercauteren crypto system, in that one starts with the representation of the ciphertext modulo Q. They are represented in the residue number system that I explained before. So the first product that we need to do during homomorphic multiplication takes place over R, not over RQ. And to prevent this, to prevent multiplications from wrapping around modulo Q, we first extend it to another basis that I call RB. And now this product, I'll get the same result over RQ times RB as I would get if I were to compute this over R, because B is going to enlarge the dynamic range of the residue number system. And then I need to compute, if you remember, I need to compute the remainder of the division. I need to compute the division, sorry, it's not the remainder, the division by Q. To do this, I first extend the result of the product modulo Q from this basis to this basis. And from this, I can compute this subtraction and this division, and I get the value that I wanted. The result is only represented modulo RB, but I want the results to be in RQ, because that's the input, and this will allow me to do more multiplications. So I extend the result back to RQ, and now I process this value. I can decompose it into small values, like before. I multiply it by the realignization key. All this is done modulo RQ, and I get the result of the multiplication. This has two limitations. The first one is that there are large basis extensions that are required to do this division. And the basis extensions have a complexity that is quadratic with the number of elements in the RNS basis. So this increases complexity. And secondly, even though these values are small, when I compute their RNS representation, I need to compute the remainder of their division by each one of the moduli of the RNS set, which means that their representation is as large as the largest value representable in it, because it's non-positional, which leads to a lot of redundant computations. And so what we've proposed is to use a different representation that mixes positional representation systems with the residue number system. And so instead of choosing Q to be the product of several primes, I choose Q to be a power of a product of these primes. And so I'll have a traditional positional representation. So I have A that is the result of this operation, but each digit is going to be represented in an RNS basis, RP. However, since this is a positional representation, I need to let the digits grow after additions and multiplications, because then I'm going to need to do carry propagation. And to achieve this, I represent digits not only in RP, but also in RP. So after an addition and multiplication in this representation, I need to do carry propagation. And this is very similar to the division that we saw before. So I start by extending, so this is the digit AI. I'm computing the carry that this digit produces. And I extend AI modulo P to RB, and this allows me to compute this division. This is also going to be the new value of the digit in RB after carry propagation is computed. After computing this division, I have the carry, and I can add the carry to the next digit, AI plus 1. Right now, I still need to do carry. I still need to do basis extensions in this case, but the bases are going to be much smaller. They are d times small if I have d digits. In the end, the algorithm that we get as a result is this one. In the beginning, we have two ciphertexts that are represented in HPR. The most significant digit is only represented in RP because values larger than this, larger than P would lead to overall values larger than Q. This would be redundant because I'm operating modulo Q. So I need to extend the most significant digit from RP to RB. I do this exactly. Then we needed to compute a product between these two polynomials. We'll do this using a Karatsuba algorithm. And the advantage of having a positional number system is that now to compute the division by Q, I need only to ignore the least significant digits. And then when I do this decomposition, the small values are very easy to represent because I need only one digit to represent them. So I'm reducing the complexity of the scheme here. And then at the end, I do carry propagation to reduce the norm of the coefficients of the HPR representations. And so I inherit the benefits from RNS in that the residues can be processed independently, for instance, when I'm doing these multiplications. But I also inherit the positive aspects of the positional representation, that division is just ignoring the least significant digits, and the decomposition can be represented using a single digit. And so overall, the complexity of an FV crypto system that relies purely on the RNS is n to the cube log n. This is because after the composition, I get k elements, where k is the number of elements of the RNS basis. And for each one of these elements, they are reduced modulo each one of the bases. So I have k polynomials for each one of these elements, and I need to compute the entity for each one of them to compute the product between them and the relinearization key. And so I get a complexity that is k squared n log n. For security, I need k to be O of n, and so in the end I get n to the cube log n. In this case, since we've reduced the sizes of the representations of the decompositions of C2, they are represented as a single digit, and so I reduce the amount of entities that I need to do. And so the amount of entities that I need to do is going to be n plus epsilon, n1 plus epsilon, and then the complexity of the entities is n more than. However, the complexity now has now been moved, and it's now related to the product between the realignization key and the decomposition of CT2. And so I get the complexity.
Is n here the ring dimension or the number of bases?
No, the ring dimension.
It's the ring dimension, okay.
So we've obtained the experimental results. HPR is the scheme that we are proposing. BEHZ is a system that relies purely on the RNS, and the HPS is a system that is relatively close to this one, but they use a different base extension, and they have a better homomorphic capacity, because this one introduces a few errors during homomorphic multiplication. And for smaller schemes, for smaller parameters, this is the, so this is n equal to 13. Our scheme is slower, but as this gets larger, well, here our scheme is still slower, but the multiplication is faster, the realignization is slower, which means that in this case, our scheme would be more appropriate if you needed to compute, for instance, the addition of products, because in that case, you can compute the product, produce 3-element ciphertext for each product, and then add all of them, and then only do one realignization at the end. And for very large schemes, like 2 to the 16, our scheme is faster than the other two. And these are the schemes that I was talking about before. And this work was developed in collaboration with Jean-Claude Bajat, with Julien Nard, and Vincent Zucca. So schemes like FV, no, now I'm going to the second part of the talk. So schemes like FV provide with this technique called batching that allows you to accelerate the evaluation of multiple Boolean gates at the same time. And that's because the plain text space corresponds to a cyclotomic ring where the coefficients are reduced modulo 2. And if you choose 5 of them appropriately, then it will factor into L polynomials modulo 2. And if you want to encrypt several bits in the same ciphertext, you just need to use the Chinese remainder theorem, and you just need to create the polynomial m of x such that when you compute the reduction by f0x and 2, you get the first bit, and you do similar for the other bits. And then when you do additions, homomorphic additions, you'll be XORing these bits. And when you do homomorphic multiplications, you'll be ending these bits. And so the main question that I try to answer is there any way that you can efficiently map real world applications that operate over the reals onto this domain? And that what we have proposed to do is to represent numbers using a stochastic representations. So a stochastic representation of a value between 0 and 1 corresponds to a sequence of bits such that the probability that each one of these bits is 1 corresponds to the value that we are representing. And this leads to very simple arithmetic circuits. So if I have 2 of these sequences and I want to compute their product, I simply need to do an AND gate. They need to be statistically independent, but if they are not, then I can rotate them at random and they'll produce 2 statistically independent bits. And I can use the 2 operations that I talked about before, the XOR and the AND, to build multiplexer gates, and these multiplexer gates can support a scaled addition. This P is scaled by 1 minus S, and this Q is scaled by S. And so, okay. Now if I use batching, I can simply represent the values between 0 and 1 to map the stochastic representation into the batching slots. And then I can do those multiplications and those scaled additions using very simple homomorphic circuits. There is this algorithm that allows us to evaluate polynomials efficiently. So I just need to represent polynomials using Bernstein polynomials, which is just a different base to represent polynomials. And then there is this algorithm that is called the Stochastic algorithm that has an inner loop. We can interpret this J loop as doing this operation that converts a polynomial of degree J into a polynomial of degree J minus 1 that when evaluated at x0 produces the same result. So when I end this, I have a constant polynomial that will be the result that I want. And at the core of this algorithm is the operation that we saw before. This is the scaled addition, where the S corresponds to this x0, and this will be P and Q. So I can do it homomorphically with the stochastic representation. And so, as a use case, we've considered image processing because stochastic representations are inherently noisy, and so we need to consider applications that are robust to noise. And image processing is one of those applications because typically our eyes can tolerate a certain amount of noise. So we've considered the negation of an image. The pixels were all mapped to the 0-1 range, and then we've operated over these bits, and then we've retrieved the images back from the result. And then we've approximated the high pass filter by doing something that's close to a subtraction, and then low pass filters were basically added. We added neighboring pixels using a tree of muxes. So we've gotten some results. This has been replicated from the state of the art. So they use different platforms. It's not possible to directly compare the two. And this scheme uses a payday crypto system. Although it's not possible to directly compare the two, I would say that ours achieves much better performance. What's interesting here is also that in our case, encryption is faster than decryption, which means that it's probably better for operations where you need to combine multiple images, say, for instance, blending several images, whereas in their case, their decryption is much more efficient than encryption. So if you want to encrypt one image and apply several filters to it, then probably their scheme is more optimized for that.
How big an image?
The images were 256 by 256 by 256 pixels. This is the related array. And so this has been, this is the third part of my talk. I'm going to discuss whether it's possible to derive algorithm-hiding fully homomorphic encryption in an efficient way. There has been one proposal to achieve this in the literature, where they suggest to describe a general purpose CPU as an homomorphic circuit. And in this way, as a client to, say, a cloud computing scheme, I can provide the cloud with a program memory that is encrypted, and then the cloud can evaluate this circuit cycle by cycle, and they won't know what program they're executing. And in the end, they send me back the data memory. I decrypt the data memory, and I get the result from the program that I sent and from the data that I sent. However, the problem with this approach is that the evaluator does not know which instruction is executing, so he needs to execute the whole circuit. This is very expensive. In particular, you need to do memory access and those kinds of things. A second problem is that the evaluator, since they do not know what instruction is being executed, they don't know when to terminate computation, which makes this scheme a bit impractical. And so what we propose instead is that we analyze the efficient structures that one can obtain from homomorphic encryption, and then we provide an algorithm hiding fully homomorphic encryption, but that focuses on this small set of applications that can be efficiently evaluated with fully homomorphic encryption. And so we've considered two structures. The first one is the structure that I talked about in the second part, that uses stochastic computing. And then the other one that we saw allows for the processing of fixed point arithmetic. As far as I know, it cannot be applied to FV. It was built based on BGV, which is shares some properties of FV, but the ciphertexts are represented. Well, they are also represented as two elements from a cyclotomic ring. In this particular case, when you evaluate that those polynomials at y equals to s, you basically get the message plus some noise. And here they interpret the noise as a noisy representation of the message. And so to cancel out this noise in a certain way, they scale the message by delta. This delta is different from the delta that we saw in FHE. It's much smaller. And you can see that after additions, this structure is maintained. After multiplications, there will be a delta squared factor. And to scale down this factor, they use the modulo switching from BGV, but in a different way. They basically scale this into a smaller ring. This ring should be delta times smaller than the initial ring. And so the message will also be scaled down by delta. And the amount of operations that you can do is limited by the amount of times that you can reduce the ring. And we saw before that we can evaluate polynomials efficiently using a stochastic representation. It's also evident that you can use the other schemes, since you can do additions and multiplications. You can use Arner's method for the evaluation of a polynomial. And so what we suggest is to use basically Weierstrass's theorem and consider all multivariate continuous functions. When you evaluate these functions at these points, we get coefficients for Bernstein polynomials that approximate this function. And well, when this n1, etc., and n tend to infinity, then this approximation will tend to the function that you're approximating. An advantage of this approach is that I'm evaluating this function in kind of a black box manner. So a user of our library does not need to change the way they develop their program. They just need the result of the programming to be a continuous function so that we can approximate it. If I'm using stochastic computing, then I can use this representation directly. If not, I can convert it to a power form. And then, like the papers provided with ways to evaluate univariate polynomials. Over here, we are considering multivariate functions. So we want to evaluate multivariate approximations to those functions. And you do this by rewriting those polynomials in this way. And then I can use the same algorithms that I use to evaluate univariate polynomials if I call it recursively. So each time I need to get a coefficient to evaluate this polynomial, I just call it recursively. I just call the function recursively because the coefficient of these polynomials are going to be the result of the evaluation of this polynomial, etc. And in the end, I get unitary polynomials. There is the base case that in the original proposal could evaluate. And there's a similar rationale for the power representation of the polynomial. And so what we've proposed is that for all continuous functions, you can evaluate it at certain points. I get an approximation using a Bernstein polynomial or a power form polynomial. I encrypt it. I send to the homomorphic evaluator. The homomorphic evaluator doesn't have an access to the original function, so it doesn't know what function is being evaluated. And then I do this in offline phases. During an online phase, I basically encrypt my data. I send it, and it uses polynomial evaluation to provide me the approximation of f. And what's nice about this scheme is also that we fix the problem of the evaluator not knowing when to terminate the evaluation, because he knows the degree up to which we are evaluating the function, so he knows when to stop execution. And we've considered on use case application, we've considered the sparse marks function, which is similar to the soft marks function if you're familiar with neural networks. It's basically used on the final stage of neural networks to map scores to probabilities. That's going to be the output of the classification that you're doing. And we've considered both representations using univariate and bivariate approximations to this function. We have used BGV-styled crypto systems. The main difference between the two is that fixed point representation can handle powers of two cyclotomics, which are typically more efficient because they can use entities directly, whereas for non-power of twos, the most straightforward approach is to use something like a bar rate reduction when you're doing polynomial arithmetic, which is similar levels of noise. If you take into account parallelism, they should have more or less the same complexity, because the the Castle-Joule algorithm has a double loop to evaluate polynomials, but the inner loop is completely parallelizable, so all the iterations can be done in parallel. And so that would mean that it should have the same complexity as the Horner method, if you have enough processors. And also, when you are evaluating multivariate polynomials, all those recursive calls that I talked about earlier can also be done in parallel. In practice, the amount of parallelism that you can extract limits the performance that you can attain with stochastic representation. So in the end, this is a bit slower than the fixed point representation. But the stochastic representation is more general, since it works for schemes like FV, whereas the fixed point representation, as far as I know, cannot be applied to FV. And so this was proposed as a way to do cloud computing, and over here I have a comparison of several approaches to cloud computing. There is a traditional approach where you send your data to a cloud server that processes your data. Sometimes this takes place in shared machines, so your data is vulnerable to attacks like Spectre or Meltdown. They can steal your data. If you use libraries, for instance, for partially homomorphic encryption or fully homomorphic encryption, it typically requires for you to have a strong familiarity with the underlying scheme, but they hide the data, so it prevents other people from being able to extract the data. Whereas our scheme says we evaluate the functions in a black box manner. It does not require for you to have a strong familiarity with fully homomorphic encryption. It hides both the data and the algorithm, although the performance might be a little bit worse. And then this was the initial proposal that I talked about. It's a bit impractical, but yeah, it supports most applications, so that's an advantage. And that's it. So we conclude that HPR, by allowing us to do division and volume more efficiently, and enabling the representation of small values more efficiently, is able to reduce the complexity of homomorphic multiplication. I didn't talk about it here, but it can also reduce the complexity of decryption, because now decryption also requires a division by Q, and you can approximate it just using the most significant digits of the representation. Yeah, and stochastic operations have direct homomorphic counterparts, so you can evaluate like multiplications using very close circuits, which is nice. And we proposed a scheme which, rather than trying to provide you with a way to evaluate an homomorphic circuit completely, it focuses on the small set of applications that can be efficiently evaluated with homomorphic encryption, and so it provides algorithm hiding in this small set, but at least you can do it efficiently rather than having to evaluate the full homomorphic circuit. And so the first part of this talk is included here if you're interested. The second part is in this article. So this part. That's it. If you have any questions.
Thank you.